Hi everybody, this is John Lewandowski from Case Western Reserve, and I'll be describing a project that one of our collaborators, Lawrence Livermore National Lab, is interested in entitled Stress Corrosion Cracking of Aluminum Magnesium Alloys Studied via X-ray Computed Tomography at the Diamond Light Source. As shown in the top left, what we have in our possession are plates that have been retrieved from a Navy destroyer after 42 years of service. As shown in the bottom, we've been testing some of those samples at the Diamond Light Source at the UK, where on the left, we can test in tension, but in different atmospheres, in the beamline and record the evolution of fracture, either under dry or stress corrosion cracking conditions. A lot of the tests prior to those Diamond Light Source experiments were conducted in the Advanced Manufacturing and Mechanical Reliability Center that I run at CASE. The website's shown there. For this project, Kaylee Coleman will help us analyze the images that I'll describe to you, and Rich Thomason also co-directs the AMMRC. So if you go to the AMMRC website, you'll see a lot of the different bits of equipment that we have, some of which is shown on the right. But you'll also see that we're doing a lot of additive manufacturing work funded by a number of different agencies, as shown there, as well as companies. And the focus in all those works is looking at process structure reliability relationships, including in some cases stress corrosion cracking. And as you look at the details of some of those, some of them are based on powder bed fusion, and others are more directed energy deposition and in some cases wire-based high deposition rate approaches. The alloy systems that we've been working on are those of commercial interest that include titanium alloys, aluminum alloys, copper alloys, and austenitic stainless steels. In addition, a recent project has started with ARPA-E support with the people shown, looking at refractory-based high-entropy alloys as well as variants of niobium silicon alloys. The students that are involved with each of these projects is shown on the right. The project that I'm going to talk about today is more on the structural reliability side, focusing on stress corrosion cracking of commercial alloy plate, but one that has been retrieved from a Navy ship that was decommissioned after 42 years of service. Undergraduate students also work on our projects, and those are shown on the bottom. So with regard to this stress corrosion cracking project, field retrieved ship plates from the ship shown in the top left have been obtained after 42 years of service. And what we're particularly interested in looking at is how does fracture evolve in these materials. The microstructure is shown in the middle, and we've extracted samples in the T orientation to sample the grain boundaries in a specific way. On the far right at the top, one of our collaborators is putting the tension sample into the test fixture that's in the beamline. Eventually, we'll be able to test, as shown in the bottom right. The tension sample is in there either in a completely dry or humid or even solution environment, where we can image at a variety of different resolutions depending on the objectives that are used on the right there to capture the evolution of fracture, starting at the very start with zero load and then generating stress strain curves like you can see in the bottom middle, where we take tomograms wherever you see the arrows. So initially, the people on the left bottom are watching the tomograms as they evolve. And we start to decide when we should start taking more pictures. So obviously we take them at the start because we need to characterize the starting material and structure. They're relatively infrequently taken until we start to see activity in the material. And then as you can see by the number of arrows, quite a few tomography scans are taken that are 3D in nature and very dense in terms of their imaging, in that we probably have about 20 terabytes of data even in only 2 tension tests. If you look at a sample that's broken, first of all in the SEM on the bottom left, you'll see that there are regions on that thumbnail in that sample that look like you have fracture along grain boundaries, and the grain boundaries are shown in the top left. That only happens for so long because eventually catastrophe intervenes, and that's the region in the left-hand portion of the left image. Well, if we take a tomogram of just that broken sample and look at one slice, not a 3D slice, but one slice, we can see evidence of those grain boundary fractures, as you can see that they're labeled. But we also have other information. This is a relatively low resolution scan here, but you can see there are a lot of white dots, which are inclusions in the material that are elongated along the rolling direction. There's also voids that are black that are hard to see at this magnification. So what we need to do next is to analyze the time series of images that were obtained in those tensions tests, because there we'll be able to see the failure progression on a dry situation, which is, if you will, the best the material is going to behave, and then under this stress corrosion cracking condition. So these will be 3D volumetric images and about 20 terabytes in character. And so what I've described to you is the structural reliability of materials, those second set of projects where we're looking at stress corrosion cracking of aluminum magnesium alloys. But again, highlighting that we have a lot of other additive manufacturing projects going on that may be of interest to collaborators to build on this expertise. Again, some of the equipment is shown at the right. So I've covered the bottom region here, stress corrosion cracking. We know what the material is, we've characterized it, we've tested it already under dry and under stress corrosion conditions, and we have a series of images now that show the evolution of fracture dry versus stress corrosion. And there's about 20 terabytes of images that Kaylee will be helping us along with the other members of the team. The unique aspect of this is that we also may be able to use this information to design remediation strategies. I close with, we also have additive manufacturing work going on over quite a wide regime, and that may be of interest to some of the collaborators. So again, I'm John Lewandowski at Case Western Reserve, and thank you for your attention. Bye now.